Hello, dear students. Welcome to Mass Spectrometry Lecture Session 4. In this lecture session, I am going to explain you about rules of fragmentation, how the organic compound can be converted into small daughter units or fragments. So this is a basic fundamental for the interpretation of mass spectra. Before going to the rule of fragmentation, I am going to give you some tips about how compound is fragmented. For this, I have taken the example of one aryl ketone, that is a acetophenone benzene ring COCH3. When this compound is fragmented by electron impact ionization in 70 electrovolt, first of all, it will give you a molecular ion or parent ion or a radical cation. So what is happening here is one of the electron is removed. So we are not sure from which position electron is removed. For that reason, we have put the bracket plus dot. So generally, electrons are held from the position where it is loosely held. So in this structure, there are electrons either in this pi bond or in this non-bonding oxygen. So these electrons are loosely held either from this position or this position. One electron is removed, so you are getting a molecular ion. So in this case, only the electron is removed, the number of atoms remain the same. So the molecular ion peak 120 is nothing, it is a molecular weight of acetophenone. Then next is cleavage is taking place from this position, that is CH3 is removed. So you are getting a benzene ring CO plus, that is 105, that is a acyl cations. These acyl cations are common fragments in aryl aldehyde and ketones. So carbonyl generally give acyl cations. So this 105 peak can give you basic idea that your compound may be aldehyde or ketone. Then again there is a cleavage from this position. You are getting a aromatic ring with plus dot, that is a 77 mass by charge. Then this 6-member ring is converted into the 4-member cyclic ring having a 51 mass by charge. Again it is cleaved and it will give you the open chain structure, that is CH double bond CH2 plus 27 mass by charge. And also there is a probability of cleavage from here, and you are getting a COCH3 plus, that is a 43 mass by charge. So this compound, whenever it is fragmenting, you are getting one molecular ion, then others are the daughter ions or the smaller fragments or the unit. So whenever we are interpreting any structure, you should have answer for some questions like how does organic compound fragment? What are the probable site of cleavage in compound structure? What are the probable daughter ions? What are the stability of a molecular ion and daughter ions? What is the value of molecular ion and what is the value of base? So these answers for those questions are really important whenever we are interpreting this spectra. So how organic compound fragment and what are the probable site of cleavage? Because one compound can fragment from different places. For example, here it is from the CH3, you are getting this place. Here it is from benzene ring and CO, you are getting this fragment. So both probability is there. Either breakage from here is possible, an acyl cation, and breakage from here for here position, you are getting a CH3 double bond CO plus you are getting. So probabilities are there. Those probabilities you should know. Then another is probable daughter ions. What are the probable daughter ions and what are the stability of a molecular ion and the daughter ion? Stability of the ions in turns give you the intensity of peak in the spectra. So the compound which has a higher stability, you will get a sharp peak with a higher intensity. Low intensity daughter ions with low stability, you are getting a least peak in the mass spectra. So likewise, stability of the ions are also important. Then what is the value of molecular ion? It is very much important because as we know that whenever we are getting any organic structure of any organic compound, just by adding a number of atoms, atomic weight, we can get a molecular weight. In this case, we are getting a 120. So in mass spectra, if electron impact ionization technique is we are using, then right hand side end of the last peak will be the molecular ion peak. So the 120 we should get in this spectra, that is the peak for the molecular ion that represents the molecular weight of a compound. Then it is specifically important in case of the protein and peptides, because proteins and peptides, they are formed from huge number of amino acids. We cannot interpret each and every amino acids fragment. So what we check is a total weight of the protein, number of amino acids, sum the number of amino acid, and you just go for the that peak abundance, that is the molecular weight of the protein. Then another important is the base peak. That is the highest intensity peak in mass spectra. In this case of acetophenone, the highest intensity peak you are getting is a acyl cation, that is a 105. Whenever you are getting a mass spectra and if we are getting a highest peak of 105, then we may guess that our compound may be aldehyde or ketone. So this answer for the question is very important. Here you can see this is the mass spectra. All the peaks are straight lines, so that is also known as a line spectra. So each is corresponding. This is for the molecular ion. This is 105 peak, and this is 77 peak, 51 peak, 27 peak, and the 43 peak. To answer for those questions, you should keep it in the mind whenever you are interpreting any structure in mass. Now let us start with rules of fragmentation. And generally these rules of fragmentations are rules based on the concept of physical organic chemistry. So I have mentioned altogether 11 rules of fragmentation, and we consider that whatever the ionization technique we are using is an electron impact ionization. So let us start with the first rule. The first rule of fragmentation states that whenever we are having compounds, then the straight chain compound has a highest intensity molecular ion peak as compared to the branch chain. That means straight chain compound intensity peak is more as compared to the branching in the structure. So you can see here, these are the three examples, that is a butane, this is a straight chain, then 2-methyl propane, then we have a 2,2-dimethyl propane. These are all three structures. So this is a N-butane, it is a straight chain. This is a branching is there. This is further branching is there. Whenever the branching of the compound is there, then the covalent bonds become the weak. Here you can say there is a steric hindrance also. There is a weak carbon in the center. So this can be easily broken. However, this is also easily broken, but to break this compound, we require a highest energy because the bond energy in N-butane is more. So straight chain compound have a highest intensity of a molecular ion peak or parent peak as compared to branch chain. Now moving to the second rules of fragmentation. So as we increase the molecular weight in the homologous series, the intensity of molecular ion peak decreases. So here you can see we have a structure of propane, butane, pentane, and N-alkane. Every compound molecular weight is increased by the CS2 unit, that is a carbon 12, hydrogen 2, total is a 14 atomic mass unit. So by 14 unit we are increasing the molecular weight. As the molecular weight increases, the intensity of molecular ion peak decreases. So the propane has a highest intensity molecular ion peak as compared to these compounds. Now moving to the third rules of fragmentation, that is in branch chain compound, cleavage is favored that give rise to stable carbocation. So as we know that in fragmentation we will break a compound or we are getting a carbonium ion or the carbocations. So as we know the chemistry of a carbocation, 3-degree carbocation is more stable than 2-degree and 2-degree is more stable than 1-degree. So here there is a structure of 2,2,3 trimethyl pentane. So in this condition, first this compound is converted into the molecular ion. Now further fragmentation is there. So here from this position fragmentation is taking place. When from this position fragmentation is taking place, this positive charge is possessed by this tertiary butyl carbocation, not by this secondary CH group. The reason is in tertiary butyl carbocation we have a 3-methyl groups. So these 3-methyl groups are the electron donating group or a electron releasing group. This methyl group will release electron to this carbon, center carbon. This methyl group will also release the electron to the center carbon, and this methyl group is releasing to this center carbon. So altogether this positive charge is decreased and the stability of this carbocation is increased. So the favorable will be the tertiary, not a secondary. And another structure, that is a 2-methyl butane. So whenever cleavage is there, cleavage is from this position. So when from this position cleavage is taking place, this isopropyl cations possesses a positive charge, not a ethyl cation. Ethyls become a free radical because ethyl is a primary, while the isopropyl is a secondary because there is a 2-methyl electron donating group. This positive charge stability will be increased. So this is how you should know the stability of carbocation. This is 3-degree is more stable than 2-degree and 2-degree is more stable than 1-degree. That is basically depend on the number of electron donating methyl group. Here there are 3 electron donating methyl group. Here there are 2 electron donating methyl group. Here there is only 1 electron donating methyl group is. So whenever fragmentation is there, the possibility is the tertiary carbocation formation is more as compared to secondary. Secondary carbocation is more as compared to primary. The fourth rules of fragmentation, it states that in case of double bond aromatic compound and heteroaromatic compound, we will get a high intensity molecular ion peak. This is because of the delocalization of electron and resonance. For example, if we take a benzene, in this benzene, when it is ionized, it will form a molecular ion plus dot. This plus dot charge can be delocalized in this free alternative double bond of this benzene ring. So first case plus dot in this position, second case in this position, third case in this position. So altogether there are 3 resonance structure possible for this benzene. So the stability of this benzene compound is increased. Hence in aromatic, heteroaromatic and double bond, due to the resonance as well as the delocalization of electrons, there is a prominent molecular ion peak is observed. Then rule number 5 of fragmentation, it states that whenever there is a alkyl benzene, there is a cleavage of carbon-carbon bond beta to the aromatic ring, and this leads to the more stable propylene ion. So here you can see this is a benzene. So this benzene CH2R, from this carbon center of the benzene aromatic ring, this CH2 is a alpha and this R is a beta. So this, in between this there is a cleavage. So you will get a CH2 plus benzene, that is a benzyl cations which has a mass by charge of 91. However, the most stable cations is produced by the cyclization of this compound. This CH2 will participate in cyclization of the 6-member aromatic ring to the 7-member cycloheptatrienol ions. So 6-member ring is converted into 7-member ring. Then this R is removed and you are getting a propylium ion which has a mass by charge 91. This propylium ion is more stable as compared to the benzyl cation. However, both has a mass by charge of 91. Similarly, if we take the example of 3-alkyl pyridine, so this is a pyridine ring. This nitrogen is 1, this is second position. In third position, there is a alkyl substitution, so 3-alkyl pyridine. When this is clipped or fragmented, this CS2 will participate in this aromatic system, and this 6-membered ring is converted into 7-membered heterocyclic ring containing nitrogen, which we called as a propylium ion. Now let us discuss about rule number 6. It is related to the unsaturated compounds or the alkene type of compounds. Whenever there is a alkene type of compounds is there, the cleavage is from beta position to the double bond. This is a CH adjacent to this. This is CH2 and this is R. So this is alpha and this is beta. From this position there is a cleavage. So whenever we carry out the electron impact ionization, first of all the loosely held electron in this double bond is removed. So this I have mentioned at dot 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 plus. This plus indicate one double bond electron is removed, we are getting a parent ion. Then there is a cleavage from this beta position, that is adjacent to this CS. This is alpha carbon and this is beta. So here from R dot is removed, we are getting a CS2, single bond CS, double bond CS2. This double bond can shift here and this positive charge can shift to this carbon. We are getting this carbocations. So these are known as allyl cations. Adjacent to double bond CH group carbon is known as allyl carbon. Here the allyl carbon has a positive charge, that's why it is known as allyl cation. Now, rule number 7 is related to another unsaturated compound in a cyclic ring structure, that is, for example, cyclohexene. When this cyclohexene undergoes fragmentation, it will give you the retro-dialsalder product. So when this compound is ionized, we are getting a molecular ion plus dot. Then this double bond electron will shift here, it will shift here, this bond electron will shift here, it will shift here. You are getting a 1,3-butadiene radical cation and the ethene. So generally, Diels-Alder reaction is known as a cycloaddition reaction, and it is a type of pericyclic reaction where when we react 1,3-butadiene with ethene, we are getting a cyclohexene. If we move this direction, it becomes a Diels-Alder reaction. That is a 1,3-butadiene react with ethene, you are getting a cyclohexene. When cyclohexene we fragment and we are getting a 1,3-butadiene and ethene, it becomes a retro-Diels-Alder reaction. Now moving to the another rules of fragmentation, it is related to the heteroatoms. Whenever in the structure we have a heteroatoms like Y here, this Y may be oxygen or sulfur, as it is a divalent, it may be a oxygen or sulfur. Some cases it may be a nitrogen when it is a trivalent. So here it may be oxygen or sulfur. So when the heteroatoms are there, the cleavage is from the carbon next to heteroatom. So this is why this is another carbon, this is another carbon. From this position cleavage is taking place. First of all, when we are carrying out the ionization, the electron, one of the electron from heteroatoms will remove, and we are getting a parent ion, that is a CS3 CS2Y plus dot CS. Then the cleavage is from the carbon next to heteroatom, that is from this position there is a cleavage. CS3 dot will remove, we are getting this structure. This positive charge can shift here and this double bond electron can shift here, you are getting a resonance stabilized structure like this. These are the two probable resonance structures. Whenever there is more than one heteroatoms in your organic compounds, for example, this is a 2-amino ethanol where there are two heteroatoms, oxygen and nitrogen. First, it is giving a molecular ion peak. When it will fragment, then it will gives a fragment containing nitrogen with a positive charge or fragment containing oxygen with a positive charge. So it depends on the electron donating nature of a nitrogen. The atoms which are more electron donating in nature, that will be formed in a highest number. So this nitrogen is more electron donating than the oxygen. So nitrogen containing fragment is 57% as compared to oxygen containing fragment of 30%. Then another rule is a nitrogen rule. So the nitrogen rule is based on electron impact ionization. Whenever in the mass spectra, if we are getting the molecular ion peak weight in even number, then it has an even number of nitrogen or no nitrogen. If molecular ion peak is odd number, then there will be a odd number of nitrogen. You can see here in this table the number of nitrogen, there is no number of nitrogen is 0. In case of methane, chloroform and 16 fullerene, there is no nitrogen in this structure. So according to nitrogen rule, the molecular weight should be even number. So you can see 16, 118 and 720, these are the even number. When the molecular weight is even, it has an even number of nitrogen. It means that the molecular weight of pyridiazine, where there are two number of nitrogens, it has a molecular weight of 80. That is a even number. Similarly, when molecular ion peak weight is odd, then the odd number of nitrogen is present. So here in ammonia, the molecular weight is 17, that is an odd number. So it has an odd number of nitrogen, that is a 1. Similarly, in pyridine, there is a molecular ion peak 79. This is an odd number, so it has an odd number of nitrogen, that is a 1 nitrogen. Similarly, in triazole, there are 3 nitrogens, that is an odd number, 3 nitrogens. Its molecular weight should be odd, that is a 69. So this is known as a nitrogen rule. Rule number 10 is for the saturated ring system or the cyclic structure. In this saturated ring system, whenever there is a alkyl substitution is there, the cleavage is from the alpha position. So this is a carbon center, this R is a alpha group. From this position, there is a removal of the R dot and the cyclic structure will possess a positive charge fragment. The another most important rules of fragmentation is the rearrangement. Generally, certain compounds they can undergo the rearrangement within the molecule, that is the intramolecular rearrangement, and that cannot be explained from the general rules of fragmentation. So most of the time there is a migration of the protons or the atom from one position to another position, and it will give a more stabilized structure. And one of the most common rearrangement reaction is known as a McLaftree rearrangement. In this McLaftree rearrangement, which is common in acid, aldehyde, amide and ketones, to undergo the McLaftree rearrangement, there should be certain condition in the structure of a compound. First of all, it should have a heteroatoms. There must be one double bond and there must be one gamma abstractable hydrogen. If these three conditions satisfied, then it can undergo the McLaftree rearrangement. Now I am going to explain you the mechanism of McLaftree rearrangement. For that I have taken one compound. This compound satisfied McLaftree conditions because it has a heteroatoms oxygen. There is a pi bond or double bond, that is a C double bond O. Then we have a gamma abstractable hydrogen. If we consider this carbonyl carbon adjacent to this, it is known as alpha. This CH2 is a alpha, this CH2 is a beta, and this carbon is a gamma carbon. Whenever there is a McLaftree rearrangement, this hydrogen will shift to this oxygen, so it will form a OH. When this hydrogen shift here, this double bond will shift to this position, and this single bond carbon electron will shift here. So there is a cleavage from this position, so that when this electron shift here, there is a removal of the alkene, that is a CH2 double bond Cr2 is removed. When alkane is removed, we are getting a make left tree rearrangement fragments. And this make left tree rearrangement fragments has several resonance stabilized structure. First of all, this double bond electron will shift here. So this oxygen will become a positive charge, and there is a formation of new bond between carbon and oxygen. Then again this double bond carbon oxygen will shift to this oxygen. So this carbon will have a positive charge. There are these three possible resonance structures shown in this diagram. So what we have to remember that as it gives a number of resonance stabilized structure, generally McLeod fragments behave as a base peak or highest intensity peak in mass spectra. Now you can look at this structure, just you change Y with different atoms or groups. For example, if Y is H, it becomes COH aldehyde. Y equal to R or CH3, it is a ketone. Y equal to OS, that is a COOH, that is a carboxylic acid. If NH2, CONH2, it is amide. If OR, it is a ester. So any aldehyde, ketone, carboxylic acid, amide or ester that has a gamma extractable hydrogen, they can undergo McLeod rearrangement. For example, if we take a carboxylic acid, you replace this Y with a OH. So it becomes a carboxylic acid. So this fragment, why we have placing the OH, so we are getting McLeod fragment like this. So oxygen has a 16, carbon has a 12, and hydrogen has a 1. So you go on adding all the atoms, you will get a 60 mass by charge. So carboxylic acid having a gamma hydrogen can give a McLeod rearrangement fragment of 60 at mass spectra, and this 60 behave as a base peak. And just in place of OH, if we replace a hydrogen, it becomes a aldehyde fragment. If hydrogen is there, you just remove 16 minus from this 60, then it will be a aldehyde McLeod fragment. This is how McLeod rearrangement is taking place in any carbonyl compound that has a gamma extractable hydrogen. Thank you for patiently listening my lecture on rules of fragmentation. Have a great time and stay safe and healthy. Thank you.